L'Hopital's rule. So L'Hopital's rule actually is going to help us solve limits back from chapter 2. And you might be thinking, well, why are we going back to limits now? Well, it's because L'Hopital's rule uses derivatives to help us solve limits, and it's actually a fan favorite among students, so they love using L'Hopital's rule. And they always ask me, well, why didn't we learn this a long time ago? Why didn't we learn this first? Well, we didn't know how to take derivatives back in chapter 2. That was chapter 3. So now we're going back and we're going to apply L'Hopital's rule to certain types of limits. Now, the major mistake is that students don't check to make sure that the original function had an indeterminate form before they tried to use L'Hopital's rule. They just jump right into it because it is a nice rule that we can apply. But let's read the hypothesis. If f of x over g of x has the indeterminate form 0 over 0 or infinity over infinity, when we substitute in x equals a, or when we evaluate at first the limit as x goes to infinity, then we can apply L'Hopital's rule, which says that the limit as x approaches a of the quotient f of x over g of x is the same as solving the limit as x approaches a of the derivative of f of x over the derivative of g of x. And it works the same way if x is a limit at infinity or negative infinity. So instead of taking the limit of the original f of x divided by g of x, we can take the derivative of f of x separately from the derivative of g of x. The derivative of the numerator separate from the derivative of the denominator. That's only if direct substitution first gives us an indeterminate form. Then we can take the derivative of the top and bottom separately. So we're not thinking about this as the quotient rule. And then we're going to evaluate the limit again. So now we're going to go ahead and see this in action. Alright, we want to use L'Hopital's rule to evaluate the limit as x approaches 1 of x cubed minus 1 over x minus 1. So the first thing we have to try is direct substitution. So substituting in 1 would give us 1 cubed minus 1 over 1 minus 1, which is 0 over 0. That is an indeterminate form. So it tells us that we have to do more work. Now, typically, prior to L'Hopital's rule, the more work we would have had to do is factor. And we'd actually have to factor the numerator, x cubed minus 1, as the difference of cubes, which has its own formula. That is actually kind of long and tedious to try to memorize. But now that we have L'Hopital's rule says this, and I'm going to be really formal about it. The limit as x approaches 1 of x cubed minus 1 over x minus 1 is the same as the limit as x approaches 1 of the derivative of the numerator. So the derivative of x cubed minus 1 is 3x squared over the derivative of x minus 1 is 1. So we're taking the derivative of the numerator separate from the derivative of the denominator. So this limit is the same as this one. So what I like to do, and what I'm going to ask you to do so that I know what rule you're employing, is from one limit to the next, if you're using L'Hopital's rule, above the equal sign, put a little LH for L'Hopital, so I know what you're doing to go from one step to the next. And now we're going to evaluate this limit using direct substitution. So the limit as x approaches 1 of just 3x squared, because over 1 is the same as just 3x squared, well, I can just go ahead and plug in the 1. So 3 times 1 squared over 1 is just 3. So the limit here is 3. So that's a lot easier than trying to factor the numerator and cancel the factored version of the numerator with x minus 1 in the denominator. We can just say that the answer is 3. So let's try another example. Use L'Hopital's rule to evaluate the limit as x approaches 0 of e to the x minus 1 over cosine x minus 1. So again, we try to use direct substitution first. So e to the 0 minus 1 over cosine 0 minus 1. So e to the 0 is 1, minus 0 doesn't do anything, and then minus 1. Cosine of 0 is 1, so I get 0 over 0. Yes, it's indeterminate form, so I can use L'Hopital's rule. So I have the limit as x approaches 0 of e to the x minus 1 over cosine x minus 1. So I'm going to use L'Hopital's rule. Above my equal sign, I'm going to write LH. So now we're going to do the limit as x approaches 0. I have to take the derivative of the numerator. The derivative of e to the x is e to the x minus x, so the derivative of minus x is minus 1, and the derivative of negative 1 is 0. All over the derivative of the denominator, the derivative of cosine x is negative sine x. The derivative of negative 1 is 0. So now I try to evaluate this new limit using direct substitution. So if I plug in 0 for this x, I'll get e to the 0 minus 1 over negative sine 0. E to the 0 is 1, so 1 minus 1 over sine 0 is 0. So I have 0 over negative 0, which is 0. I have 0 over 0 again, which is indeterminate. So I can use L'Hopital's rule again. So let's go ahead and try to take the derivative of the derivative this time. So now the derivative of e to the x minus 1, and I'm using L'Hopital's rule again, is just e to the x, because now the derivative of negative 1 is 0, over the derivative of negative sine x is negative cosine x. And now let's try direct substitution. So substituting in 0, I'll get e to the 0 over negative cosine 0. E to the 0 is 1, cosine 0 is 1, and there's a negative there. So the final answer is negative 1. So the purpose of this example is, for one, we can use L'Hopital's rule more than once, and two, we may not actually even be able to solve the original limit using any methods we previously had. So here, I'm sure there's some maybe trig identity. I could multiply by the conjugate of the denominator to try to make this solvable, but it's going to be a lot more effort if even we can solve it. But here, the obvious method, now that we know it, is going to be to use L'Hopital's rule because we got out an indeterminate form. Alright, so now we're going to try L'Hopital's rule evaluating a limit at infinity. So here, trying direct substitution would mean, well, what happens to just x squared minus 1 when x values go to infinity? Well, when x values go to infinity, if I take big numbers and square them and subtract 1, the top is still getting really big and positive. And here, if I plug in infinity, or plug in is not the right word, if I evaluate the denominator at infinity, well, these numbers are just going to get really big as well. So I get infinity over infinity, which is indeterminate. So I can apply L'Hopital's rule. The limit as x approaches infinity of x squared minus 1 over 3x squared plus 3x. If I apply L'Hopital's rule, is the same as the limit as x approaches infinity of 2x over 6x plus 3. And I can try thinking about what happens as x values go to infinity again. So 2x would go to infinity, and 6x plus 3 would go to infinity as well. So let's try L'Hopital's rule one more time, and this would be the same as the limit as x goes to infinity of 2, the derivative of the numerator, over 3, the derivative of the denominator. So 2 over, I'm sorry, I got ahead of myself. 2 over 6, which simplifies to 1 over 3. So this is the same as the limit as x approaches infinity of 1 over 3. So the limit of a constant is just the constant. So the answer is 1 over 3, which, yes, we definitely didn't need L'Hopital's rule to solve this problem. The degrees matched in a limit at infinity, so the answer would just be 1 over 3 to begin with, but just to show that L'Hopital's rule does work with an indeterminate form of infinity over infinity as well. Alright, in this last example, we're told to evaluate the limit as x approaches 1 of x squared minus 1 over x squared minus 4x. Now this is the warning example. So what we should try to do on every problem that's a limit as x approaches a number first is use direct substitution. So let's do what we're supposed to do first. So we plug in 1. 1 squared minus 1 over 1 squared minus 4 times 1. 1 squared minus 1 is 0. 1 minus 4 in the denominator is going to give us a negative 3. 0 over a number is 0, so the final answer is 0. Now, it might seem pretty obvious because we just went through it, and yes, the right thing to do is to always try to plug in the 1 first. But some of you might have seen this problem and thought, I should factor it first. So the top does factor into x squared, or x plus 1, x minus 1, and we can factor an x out of the bottom. But now that we have L'Hopital's rule, a lot of students are going to jump to trying to use that without even trying to plug in the number. Or maybe they would just plug in the 1 to the top and figure, oh, well, that's 0. It's going to be indeterminate. Let's see what would happen if we tried L'Hopital's rule, knowing that the answer is 0. So if we try L'Hopital's rule, then we'd have the limit as x approaches 1 of 2x, the derivative of the top, over 2x minus 4, the derivative of the bottom. Well, now let's plug in 1. 2 times 1 over 2 times 1 minus 4. So we'd get 2 over 2 minus 4, which is 2 over negative 2, which is negative 1, which is not the same as 0, obviously. So my point here is you have to try direct substitution first. Even if it's a longer problem than this and it seems tedious and annoying to plug in 1 first, that's always going to be a fake out. Is to make you think what's worth factoring it first or worth trying to use L'Hopital's rule first, and then falsely giving you the impression that the answer using L'Hopital's rule is the correct answer when you didn't satisfy the hypothesis first. So you need indeterminate upon direct substitution to even use L'Hopital's rule.